All right, in this video, I'm going to talk to you about lines and planes in three-dimensional space. And if you were in my linear algebra class, you're probably pretty familiar with these concepts, but I'm going to extend it a little bit and talk to you about some areas. So I think that I am assuming, pretty good amount of familiarity with vectors, their addition, multiplying them by a scalar, kind of the visual representation of them. I know that's in the pre-calculus class, so I am just assuming you know a little bit about that. So I'm not going to talk about addition and scalar multiplication and things like that. But I will go back and I will remind you about the dot product and the cross product, and then I'll show you a couple of things we can do with them. And I'm just looking for my green marker. So, definition of dot product. If A and B are elements of Rn, which means that they are n-dimensional vectors. They are vectors that have, oh no, my laptop has come unplugged and it had 5 minutes left. That would have been disastrous. Okay. If A and B are n-dimensional vectors, meaning they're vectors that just have n components in them, then A dotted with B it's a way that we can multiply vectors and get back a number. What it really does is it measures their relative lengths and how they sit with respect to each other. Okay, two vectors that are orthogonal or perpendicular are going to have a dot product of 0, but you'll see that more in a bit. And so what it is we take the corresponding components of each vector, multiply them, and then add all of those together. So it's the sum as I runs from 1 up to n of AI times BI, where AI is like, the ith component of A. So I'll just do a little quick example for you. If x is equal to, and I will continue probably to write these vectors vertically because that's just, my preferred way. If I say x is 1, 2, 3, and y is 10, 100, and -1, then x dotted with y is equal to, 1 times 10 plus 2 times 100 plus 3 times -1. So that's going to be 10, 210, 207. What I can tell you is that because the dot product is 207, I can tell you for certain that these two vectors sit at an acute angle, because of this theorem that I'm about to write down. Now, I'm not going to prove this one for you today in this video. It's something that, yes, there are people in here that were in my pre-calculus class. This was a long time ago, but if you were in my pre-calculus class, I did prove this for you. It goes back to the law of cosines. And so the relevant theorem for the dot product, you might remember this from the first semester because I definitely used this in the linear algebra course, is that A dotted with B is equal to the length of A times the length of B times the cosine of the angle that sits in between them. Okay, so where I've got basically here's A, there's B, and this is the theta I'm talking about. Okay, that's going to be relevant to us. Don't really exactly remember how it's going to be relevant to us, but I know that we will need it. Okay, then I will define the cross product. So if A and B are three-dimensional vectors, we're only going to cross three-dimensional vectors. Let's see. And this is kind of a slippery beast to define. Like, we can show you how to compute the cross product, but actually defining it is kind of unpleasant. So I think what I'm going to do is I'm going to define it in terms of a determinant, which is something we studied in the last semester. And if you were not in the linear algebra course, it's okay. I'll show you how to compute the cross product. I'll tell you what it means, and then you'll just be happy with that. Okay, so it's equal to the determinant of the matrix that has the unit vector I, the unit vector j, unit vector k. I'm realizing is, early video in this course, I might need to go over here and remind you what I, j, and k are. I is the unit vector in the x direction. J is the unit vector in the y direction. Let's see, okay, I think I do have enough room on camera to put that in there. K is the unit vector in the z direction. Okay, so that it's the determinant of the matrix I, J, and K, A1, A2, A3, and B1, B2, B3. And how you compute it, I think I'll just show you an example. And if you need more support on computing cross products, I would just direct you right to YouTube. Go up there, search computing cross products, and it'll be all right. All right, so for example, I'm going to cross the vector 1, -1, 4 with 2, 3, 0. And before I do that, I'm going to tell you that if you take, the cross product is the thing that it takes in two vectors, and it's going to give you a third vector that's orthogonal to both of the originals. Okay, so maybe I'll use the markers. So if I'm going to cross purple with black, kind of looks blue on the video. So I'll grab the green one. It observes the right-hand rule, so it's going to go up like this. Okay, if I did black crossed with purple, it'll be this vector down here. Now the length of the cross product is equal to I believe the product of the lengths, may be adjusted by the sine of the angle between them. And let's see, what else do I need to say about the cross product? I don't know. If I think of it, I'll just throw it in. But how do we do this? We're going to set up the matrix I, J, K, 1, -1, 4. And it is important that you put the one that you're crossing on the left first because, that was what I was going to say. The cross product is anti-commutative. You could even see that from my right-hand rule with the markers that the A crossed with B is going to be the negative of B crossed with A because of the way the right-hand rule works. So 2, 3, 0. And so this is going to be what you do is you're going to take I, and we're going to multiply that by a kind of subdeterminant. So we're going to cover up the row, the column and the row that I have. And then we're going to do what, most of y'all had called the fish last semester, but we're going to take -1 times 0 minus 4 times 3. So 0 minus 12. So it's I times 0 minus 12. Okay, it alternates positive, negative for linear algebra reasons. And so it's minus j times, okay, we're going to cover up the row and the column and do that same fish. It's going to be 1 times 0 minus 4 times 2. So 0 minus 8. And then we're going to add in k times, we're going to cover up the column and cover up the row, 3 minus -2. So this ends up being -12i plus 8j plus 5k, which is the same as, okay, so I'll just say -12i plus 8j plus 5k. Okay, and this is a very physics way to write a vector. Okay, it's kind of just a lot for me to write down, so I might just abbreviate that as -12, 8, 5. That's how we take the cross product. Okay, I'm going to do a couple of more examples, and it's something involving area. So just set that up. Okay, so one thing I want to show you about the cross product is how we would find the area of a parallelogram in space. Okay, that's kind of one application of the cross product that I don't think I've mentioned in this class thus far. Don't think I mentioned it in pre-calculus, but it is true, is that the area of parallelogram P is the length of U crossed with V. It's the length of the cross product of the two vectors that span the plane. So that'd be the length of u crossed with v, right? Because you take the cross product of two vectors, you're going to get a vector back. And then we can take the length of that vector, okay, which I might just go ahead and remind you how you find the length of a vector, you know, in case it had been a while or something. If v is a vector in Rn, then the length of v we can find by taking the square root of the sum of the squares of the components. You do the Pythagorean theorem, okay? I'm sure you can go and look up a video, an animation of a rectangular prism, and how the diagonal of that you would find by doing the Pythagorean theorem twice. And then it ends up just being, you know, kind of what you expect. So it's I equals 1 up to n of the squares of the components. So vi squared. And so I might do a nice example. Maybe I should do one that, like, I know what the area of the parallelogram is, right? So I might say, all right, this is a little risky, but I'm going to try to draw a three-dimensional figure while I'm recording. Okay, that's my x-axis, my y-axis, and my z-axis. I like to think about the xy plane sitting like this and z going up and down above it. Okay. There are other ways to draw this, but this is just kind of what I want to do. So I'm going to just do something like, it's a rectangle, because a rectangle is a parallelogram. So I'm thinking maybe I'll take x out to, like, I don't know, say 3, and y out to 5, and it had better, you know, come back with an area of 15. And I'm hoping that's supposed to be a right angle. That was not great, but you know, it's the best I got. See, how does it look on camera? It looks much worse. All right, I think it's mainly because this is not sitting parallel. That's my main problem. Okay, maybe that's a little better. But, okay, I know that this vector is 3 in the x direction, 0 in the y direction, and 0 in the z direction. And then the other one is going to be 0 in the x direction, 5 in the y direction, and 0 in the z direction. Okay, so I'm going to cross them. And maybe I'll just say that if I cross them, and I'll do the calculation over there. 3, 0, 0, 0, 5, 0. Just do this real quick. Okay, I times 0 minus 0. Minus j times 0 minus 0. Uh-oh. Plus k times 15 minus 0. Okay, and if you look at it and you think about it for a second, that should make sense, right? That we cross something on the x-axis with something on the y-axis, and we get something that goes in the positive z direction, if you're fluent with the right-hand rule. Okay, I'm not very fluent in physics, but that is obviously something I picked up. And you can see that if it just runs along the z-axis, this is going to have a length of 15. But I can show you the length of what I'll call, you know, a crossed with b, just for, is going to be the square root of 0 squared plus 0 squared plus 15 squared. No, that is 225. I do know that. But even if I didn't, you know, it's the square root of 15 squared is going to be 15. Okay. That's one thing we can do with the cross product. Another thing that I can do with the cross product is find the area of a triangle in space given 3 points, which is something I'm trying to remember if you can figure out how to do that without this. I think you can, but it's just not nearly as easy. This is where I would normally be like, okay, anybody got any ideas for how I could find the area of a triangle using this technique? But I don't have so many people in here, so I don't want to put anybody on the spot. Anybody just see what I'm going to do?
You're going to do the exact same thing and then divide it by...
That's exactly what I'm going to do. I'm going to just say, oh, I got a parallelogram, but really what I'm interested in is half of it, so I'm going to do that. So this is just another example. Let's look at, I thought I had an example. Of course I did not. Just a moment. I just want one that's going to have a pretty decent have a pretty decent, yeah, 104. I found an example. So this is the point 104. That's going to be the point, let's see, 0, -1, 3. And then this is going to be the point 1, -1, 0. Okay, so at this point you kind of have a choice you can make, you know, which one's going to be the two vectors I'm going to cross, right? Because you can choose these two, you can choose these two, or you can choose those two, right? What I would think is probably, I would like to start with the one that has like the most negativity in it or something, you know, so most of my vectors would be positive, fewer negative numbers to work with, fewer opportunities to make an old-fashioned calculation error. What I'm going to do, I'm going to probably choose this one to start from because I like how it's got a -1 and a 0 here. I think the calculation should be pretty easy. So I'll call this one U and I'll call this one W. I've got U equaling, okay, to go from 1 to 1, I did not change X, there would be 0 change in X. To go from -1 to 0, I increased by 1 in the Y direction, and to go from 0 to 4, I increased by 4. And then W, make sure I'm not blocking what I'm writing. No, I'm not. W is going to be, okay, how do I get from 1 to 0? I lost 1. -1 to -1, no change. 0 to 3, increased by 3. Okay. So I'm going to take U crossed with W, I'm going to find the length of that, and then I'll divide it by 2. Okay, so U crossed with W is equal to the length, or the determinant of I, J, and K, 0, 1, 4, and -1, 0, 3. And while I'm doing this calculation, I'm going to remark that it doesn't matter if you do U crossed with W or W crossed with U, because we're taking the length of that vector. And so if it's just the negative of the other one, it's kind of the same length, right? So it'll be fine. All right, anyway. So I've got 3 minus 0 on the I front. On J, I've got negative of 0 minus -4. And plus K times 0 minus -1. No, this is not a Pythagorean triple because 3, 4, or a Pythagorean quadruple because 3, 4, 5 is a triple. So I don't know about that. Okay, so the length of U crossed with W is going to be 9 and 16 is 25 and 1 is 26, meaning that the area of my parallelogram is going to be square root of 26 divided by 2. I mean, not my parallelogram, my triangle right here. This triangle has area square root of 26 divided by 2. I got it. Hold on, yes?
Sorry, what's the difference between putting the line over all of it and...
Oh, so yeah, that's kind of a subtle distinction. Especially at the beginning, I'd like to write the over arrow all the way over the cross product to give the viewer the idea that U crossed with W is a vector.
Okay, and then why do you put it in separate?
I mean,
Probably that's a more standard way. You know, it's no different.
Okay.
I'm just really emphasizing that you cross two vectors and you're going to get a vector back. I think that's all I've got for this video. Yeah, I'm going to move on to vector valued functions now. And then this is what you need to know about lines and planes in space.